Good morning. I'm going to talk about the couple criterion of finite fracture mechanics, and I will focus on the formulations of this problem in the form of the optimization problem. The first formulation of the couple criterion, was proposed by Dominique and later by Pietro, and this work initiated a large amount of publications and which were able to solve problems which were not be able to solve by classical linear elastic fracture mechanics. As we know that we consider here the concept of a crack or finite length or the finite area if both criteria are fulfilled. Also, we assume that the time scale of crack onset is much shorter than the time scale where the whole structural problem under consideration is solved. In the present work, I will consider formulation of the couple criterion in terms of the optimization problem in an abstract and a quite general framework. I quickly introduced this framework 2 years ago at the European Conference on Composite Materials, and in more detail last year in the colloquium in the honor of our chairman, Dominique Leguillon. With respect to stress criterion, we consider functional, which is a function of the stress field before the crack onset, and the area or surface of the new potential crack. This functional is a homogeneous non-negative function of degree 1 of stress field defined on this potential crack surface. Sigma c is some characteristic stress parameter, usually tensile strength. F, of course, may depend on some material parameters like sensitivity to mode mixity. And we consider this potential crack surface as parameterized by a suitably chosen set of real parameters, of generally M parameters, which can describe, like Dr. Garcia said, can describe extension of the crack, or its location, orientation, etc. We consider these parameters from some parameter region A, and A0 corresponds to the initial configuration. The area for A0 is new crack is A0. This functional for the single one-dimensional crack. These are classical criteria, the point-wise criterion, average criterion, and this is the point-wise criterion taking into account the mode mixity. This is the sensitivity of the mode mixity in the stress criterion. It can be written as was shown in a similar form by Dr. Garcia in this way, where we have the nominal stress, a kind of nominal load. This is the strength parameter, and this function appears here as a function of sigma hat, which corresponds to the unit nominal stress. If we plot this stress criterion function, for example, for the situation at a stress concentration, it is typically an increasing function of the size of the crack. If we consider it for uniform stress field, it is essentially constant. And if we study crack onset at a singular point, we obtain this stress criterion function as a monotonous increasing function from zero. If we look for the incremental energy criterion, we consider two states before and after crack onset. We evaluate the change of the potential energy B as a function of this new potential crack surface. Also, we need to compute the energy dissipated in this abrupt formation of the new crack, which can depend on several dissipating mechanisms. And following Leguillon criterion of this hypothesis, the incremental energy balance leads to this necessary incremental condition. If we consider zero kinematic energy in the state zero, we arrive to this energetic condition, which can be written also in this way. That the released energy due to the new crack onset should be equal or larger than the dissipated energy in this onset. The other interpretation would be that the sum of the potential energy and the dissipated energy should keep constant or decrease at the crack onset, where R is the total dissipated energy during the load history. How we can evaluate these changes of potential dissipated energy? Standard way, we would be using the relation between energy release rate and the potential energy, but also other options are suitable. For example, we could use incremental lecturer crack closure technique, which is quite efficient and quite simple to implement, in particular in the following the work by Dr. Asia and previous talk. I think that even much more difficult is to evaluate the energy dissipated in the crack onset. This is the most simple situation where GC is the fracture energy dissipated per unit of new crack area in the linear elastic fracture mechanics. But it is under discussion currently in the community of finite fracture mechanics because more realistic and more complex functional, taking into account fraction mode mixity and several disparate mechanisms should be developed and proposed, and experimental verification of the formula for dissipated energy are if we rewrite this incremental energy criterion in the form taking into account the dependency of the potential energy on the load, on some characteristic lengths, on some characteristic stiffness, and the dissipated energy as a function of the some fracture toughness and the characteristic length, we arrive to the dimensionless function G, which is the ratio of the the kind of normalized dissipated energy and normalized change of the potential energy, and naturally appears the Brittleness number, which is a kind of generalization of Carpenter's Brittleness number. Then the energetic condition, written in the similar fashion like the stress condition, takes the following form, where here we have the energetic criterion function E, is a function of the parameter vector defining the new crack surface, which is given in the function of the Brittleness number and the square root of the function, dimensionless function. This energy criterion function are shown here for the situation at a strong singularity. It starts from 0 and is increasing. At the fixed singularity, it's a decreasing function from infinity. If you consider a classical crack situation, it starts from the finite value and it's decreasing situation. Stress, also for stress concentration, the behavior is similar like a singularity. This energy function can be computed analytically, semi-analytically, or numerically, as was mentioned by Dr. Garcia in the previous talk. We arrive using the Legion's hypothesis to this optimization problem. We need to minimize over the parametric space defining the crack surfaces the maximum of this stress and energy criterion function. We minimize it, we define as A star. This is a classical problem of the non-smooth optimization of an envelope representation. It can be reformulated using a classical trick by Rockefeller. We extend the dimension of the parametric space by 1. It's a kind of dummy variable. And we minimize this dummy variable, which now should fulfill this condition that A0 is larger than the stress criterion function and is also larger than the energy criterion function. Actually, we are looking for this position, which is in the intersection of two epigraphs. But this should be still tested numerically if it's really it's more easily to arrive to the minimizer. Basically, two scenarios are typically appear. One is we call it a couple scenario, where we look for where the minimum is defined by both criteria. In a 1D situation, we have 1D crack, it is at the intersection of this criteria function, but for more dimension, we need to look for the minimum. The other scenario is where the situation is, or solution is essentially controlled by the energy criterion, which is over the stress criterion curve, and this is, let's say, more easy to minimize. Also, we should mention that we can also have non-uniqueness in the predicted crack lengths, although we typically put in the uniform stress field that any of these crack lengths are possible, but the critical nominal load is the same. But starting from this crack lengths, any of these lengths could appear. Other option is to consider an alternative formulation which considers the potential energy and the dissipated energy and minimize this sum of this potential dissipated energy subjected to the stress condition. The stress constraint means that the total energy minimization considers only those new crack surfaces for which the stress criterion is verified for the given load. It means for a given load, we consider only those crack surfaces which fulfill stress criterion and minimize all over this restricted set of crack surfaces. Mathematically, it can be written in this way. This is the minimization of this parametric space, where we take only a subset of this parametric space, which is defined like feasible parameter region, where we take the parameter the vector value for which this stress criterion is fulfilled, and minimize only for this value of A from the feasible parameter region. Of course, this feasible parameter region depends on the load value, on the configuration, and here are the situation, how does it can change from the empty set. It can increase progressively or by jump, or it can be non-empty for any small load value. It depends on the configuration of the problem. New crack surface may appear only if there is a new crack surface which fulfills that this value is lower than the value for the A0, which is the initial situation. New crack surface can appear only where sufficiently high stresses are applied before fracture. The crack formation is inhibited if stresses are too small. Also, there is a sufficient amount of energy. This was actually the problem of the pure energy formulation proposed by Marigo and co-workers and Robicek originally, which can lead to early fracture prediction. Because theoretically, for any small load, if the bulk is sufficiently large, a load control is considered. This minimization problem, as I presented in the previous slide, can be also written in just in terms of the changes. We don't need to consider the whole values because the initial value of P and R is the same. It's not relevant in this minimization. We could also refer to this formulation as the principle of maximum excess of the total energy at the crack onset, and when this is less than zero, then there is some kinetic energy increase. This is actually what we obtain if we minimize, and this directly leads to this condition which coincides with the condition obtained by Leguion in his seminar work, because this is zero for the initial state. We can say if we relate this principle of minimum total energy with a stress condition, that this is more selected because we are looking for the minimum, and even in the classical formulation of Kaplan criterion doesn't provide the unique prediction of the crack length. Here we can obtain the unique prediction, but the critical load predicted by both formulations, as the classical and this new one, are identical. Because of the lack of the time, I will just go directly to this formulation of the principle of minimum total energy with a stress condition, which is maybe computationally more efficient. Instead of working with the parametric description of the potential crack surface, we can considering the problem of delamination at fixed surfaces, interfacing. We can define the bonding variable zeta, which is 1 for fully bonded interface and 0 for totally broken interface. And we consider variation of this zeta in time. Time can be actually a kind of loading factor in rate-independent system. We did this kind of work with Professor Robicek, but in purely energetic formulation, but we can couple it also now with this stress condition. It means we can minimize the potential energy, then minimize with respect to displacement field. This minimizer is, let's say, in the time step UK. And in the second fractional step, minimize with the sum of the potential dissipated energy with respect to zeta, but we keep zeta fixed for those point X in the interface which don't verify the stress condition. It means actually we minimize zeta only on the lower, on the part of the interface where the high stresses are applied. And this can be also generalized following the Marino's energetic formulation for fracture in the bulk region, looking for the potential new cracks in the bulk, but we will consider the minimization of total energy for a given load in the time stepping like E. The conclusion, I will just say that this some insight to the couple criterion has been proposed, and I expect that this formulation could open new theoretical and computational possibilities for the multi-cycle initiation and propagation. It can lead to a more general, efficient computational procedure, like presented by Dr. Garcia in his previous talk, and take advantage of the lot of work done by mathematicians in minimization of energy in new fracture mechanics proposed by the last 20 years. But still, in the future, other experiments are necessary to confirm general applicability of this formulation, at least to brittle materials. Thanks for your attention.